Good morning. Now we know the definition of annihilator. Okay. For any L subspace of X, we have defined the annihilator of L. L perp is equal to set of all F belongs to X star such that F of L equal to 0. Okay. Now we are going to prove. We have a remark. L perp is same as L closure perp. Okay. Now, what is L closure? L closure consists of all X belongs to X such that there exists a sequence Xn in L such that Xn converges to X. Now, L closure perp is set of all F belongs to X star such that F of L closure is equal to 0. Clear? We have to prove L perp is equal to L closure perp. For this, first we prove L perp is a subset of L closure perp. Okay. All elements of L perp are F. Okay. So you first take some F belongs to L perp. Clear? And we have to prove F belongs to L closure perp. Okay. F belongs to L perp implies F of L equal to 0. This implies F of X equal to 0 for every X belongs to L. Now you take some X belongs to L perp and we have to prove F of L closure equal to 0. Okay. For this you take some X belongs to L closure. This implies there exists a Xn belongs to L by the definition of L closure. There exists a Xn belongs to L such that Xn converges to X. Xn belongs to L and F of L equal to 0 for every F of X equal to 0 for every X belongs to L implies F of Xn is equal to 0. Okay. Now F is a bounded function. F belongs to X star, therefore bounded linear function, therefore it is continuous. Xn converges to X implies F of Xn converges to F of X. Okay, as F of Xn equal to 0 for every n, we get this limit also equal to 0. Therefore, if X belongs to L perp, we get F of X equal to 0. As X is arbitrary, we get F of X equal to 0 for every X belongs to L perp. That is F of L perp is, L closure. This implies F of L closure is equal to 0. This implies F belongs to, thus we get F of L closure is equal to 0. This implies F belongs to L closure perp. Okay. We take F from L perp and finally we get F belongs to L closure perp. This implies L perp is contained in L closure perp. Okay. Now we have to prove the next part. That means L closure perp is contained in L perp. Okay. For this you take some F belongs to L closure perp. Okay. This implies F of X equal to 0 for every X belongs to L closure. We know that clearly L is a subset of L closure. Therefore, F of X equal to 0 for every X belongs to L. Because this is true for every X belongs to L closure. That means this is true for every X belongs to L. This implies F of L equal to 0. This implies F belongs to L perp. Thus, we get L closure perp is contained in L perp. From 1 and 2, we get L perp is equal to L closure perp. Okay. L perp is equal to L closure perp. Okay. L is any subspace, then we get L perp is same as L closure perp. Okay. Now, here actually we have chosen F belongs to L. L is a subset of X star. Okay. And L perp means set of all F belongs to L is a subset of X. And L perp is set of all F belongs to X star such that F of L is equal to 0. And clearly L perp, we have proved L perp is a closed subspace of X star. Okay. L is a subset of X star, subspace of X star, and L perp is a closed subspace of X star. Okay. L is a subspace of X and L perp is a subspace of X star. Now we are starting from same rule, using the same procedure. We are starting from a subspace F of X star. Clear? We are starting from a subspace F of X star. Then by definition, this is equal to F perp is equal to set of all G belongs to X star star such that G of F equal to 0. Okay. Then F perp is a closed subspace of X star star. That is F perp is a closed subspace of X double star. Okay. Also we get thus we get F perp is a subspace of X double star. Also it is closed. This is one method to define F perp. There is another definition, and it is denoted as F. Here perp is here. I don't know actually what we call for this notation. We call this as also F perp. And here if F belongs to X star, this F perp equal to set of all X belongs to X such that F of X equal to 0 for all F belongs to F. F perp is equal to, once again, F perp is equal to, here perp is here. Okay. Set of all X belongs to X such that F of X equal to 0 for all F belongs to F. Now if you consider kernel F is set of all X belongs to X such that F of X equal to 0. Now you consider intersection of all kernel F. So for that intersection consists of all X belongs to X and F of X equal to 0 for all F belongs to F. Therefore this notation, this set is actually equal to intersection of F belongs to capital F, kernel F. Okay. And this. Now we are going to prove one corollary 3.1.8. Let L be a closed subspace. Okay. Then L perp, here perp is in upper portion and here lower portion. L perp is equal to L. Okay. That is set of all X belongs to X, F of X equal to 0 for all F belongs to L perp. Okay. So here to prove this we are going to prove L is a, we are going to show that L is a subset of L perp, and also if X not belongs to L, then X not belongs to L perp. Okay. We have L perp is set of all F belongs to X star such that F of L equal to 0. Okay, by definition. Now, by definition, L perp is equal to set of all X belongs to X such that F of X equal to 0 for every F belongs to L perp. Now, if you look at this definition, L perp is set of all F belongs to X star such that F of L equal to 0. Therefore, if you take any F belongs to L perp, for these F of L is equal to 0. Okay. Therefore, for every F belongs to L perp, F of L is equal to 0. Okay. Therefore, if you take any X belongs to L, for every F belongs to L perp, F of X equal to 0. Okay. Therefore, clearly L is a subset of L perp. Okay. Hope it is clear. L is a subspace. Okay, L is a subspace of X. Therefore, L is a here also subspace. Now we have to prove L is equal to L perp. For this we are going to prove if X not belongs to L, X not belongs to L perp. That is A is, we have already proved L is a subset of L perp. Therefore, if A is a subset of B and if X not belongs to A implies X not belongs to B, and this is true for any X not belongs to A, This implies A must be equal to B. Okay. Now suppose for every x not belongs to L closed subspace. L is a closed subspace. Okay. Given what do we get? Distance between x and L equal to D, and that must be greater than 0. What is distance between x and L? Distance between x and L is infimum of norm of x minus y belongs to L. Okay, and if this exists and that value is called, if this infimum exists, that value is called distance between x and L. Okay, y belongs to L, infimum. Okay, so we know that L is a closed subspace. Okay, infimum means some number D is called infimum, then D is a greatest lower bound. Okay, that means if D is a greatest lower, then D plus epsilon cannot be a lower bound. That means there exists a sequence yn, or you can take there exists a y such that norm of x minus y is less than, this is not a lower, this is less than D plus epsilon, and you choose epsilon equal to 1 by n. Okay, we have already proved that. Therefore, if for every x belongs to L, as L is closed, distance between x and this exists, and that's equal to D. And clearly x not belongs to L. Therefore, this distance is always greater than 0. Okay. And by corollary 3.1.7 we get there exists a sorry. I think I missed that page. Let me check. Here. By corollary, there exists a f below f such that norm of f equal to 1 and f of L equal to 0, f of x equal to D. Clearly D greater than 0, f of x equal to D implies f of x is not equal to 0. Thus we get f belongs to L perp and f of x not equal to 0. Okay. Therefore, this x cannot be never belongs to L perp. Thus we get L is equal to L perp. Hope it is clear. Okay. Now we are going to another remark, and the remark says that for any subspace L not necessarily closed, L perp is equal to L closure. That is very easy to prove. We know that L perp is equal to L closure perp. Just L closure is a closed subspace. Just apply previous result to for L perp. Therefore, L closure perp is equal to L closure. But L perp is same as L closure perp. L perp is same as L closure perp. We apply this here. Therefore, L perp is equal to L closure. Now we are going to prove one corollary, and corollary says that this corollary is same as our dual basis in linear algebra. Let x1, x2, etc., xn subset of x be a linearly independent subset of x. Then there exists f1, f2, etc., fn belongs to x star such that fi of xj equal to delta ij, And for every x belongs to span of xi, I varies from 1 to etc. n, is decomposed as x is equal to fi of x xi. Okay. Now here you first fix some I naught from 1 to 3 etc. up to n. And let L I naught is equal to span of xi I naught equal to I naught. For example, if I naught equal to 2, then L2 equal to span of x1, x3, etc. etc. X naught is not here. Okay. L1 is equal to span of all other terms. Okay. Similarly, Ln is equal to span of x1, x2, etc. xn minus 1. Clearly, x1 not belongs to L1. So, x2 not belongs to L2, etc. xn not belongs to L1. Okay. So, this set is clear for you. Okay. L I naught is equal to span of xi, I naught equal to I naught. Clearly, xi naught not belongs to Li naught. Now, we have a result. This is one problem in exercise. If E is an n-dimensional normed space, then E is complete. Okay. If E is an n-dimensional normed space, then E is complete. Now here Li naught, dimension of Li naught is n minus 1. Therefore, Li naught is complete. Now we are going to prove Li naught is closed. Let Xn be a sequence in Li naught. And suppose Xn converges to X. Now Xn is a convergent sequence. Therefore, Xn is a Cauchy sequence. Okay. Very convergent sequence is Cauchy. Okay. Therefore, Xn is a Cauchy sequence. As Li naught is complete, every Cauchy sequence in Li naught converges in Li naught. That means this Cauchy sequence converges to some x naught in Li naught. But we know that limit of a sequence is unique. Therefore, Xn converges to x here and Xn converges to x naught. This implies x equal to x naught. This implies x belongs to Li naught. Therefore, Li naught is a closed subspace. Okay. Thus, we get xi naught not belongs to Li naught and Li naught is a closed subspace of x. Therefore, we can define distance x Li naught is equal to d as in the previous case. Okay. Suppose this is d and d is greater than 0. Therefore, using corollary 3.1.7, we get there exists a fi naught belongs to x star such that fi naught of Li naught is equal to 0 and fi naught of xi naught is equal to 1. Now, what is the meaning of that? This is actually span of xi, I not equal to I naught. Therefore, clearly for each xi, I not equal to I naught, clearly each xi belongs to Li naught. This implies fi naught of xi equal to 0. Okay. For every I not equal to I naught. Therefore, fi naught of xi naught is equal to 1. Okay. If I naught is equal to 1, we get f1 of xi equal to 0. For every I not equal to 1, fi of xn equal to 1. I not equal to 2 implies f2 of xi equal to 0. For every I not equal to 2, f2 of x2 equal to 2. That means actually fi of xj equal to delta ij. Okay. Hope it is clear. Okay. Thus we get f1, f2, etc. fn belongs to x star. For each I naught, we will get a fi naught. Therefore, I naught varies from 1 to etc. up to n. Therefore, for each, thus we get f1, f2, etc. fn belongs to x star such that fi of xj equal to delta ij. Okay. Now, let x belongs to span of xi, I varies from 1 to n. Then x you can write as sigma ai xi. Okay. Now, what is fj of x? Fj of this one. Fj linear implies fj of x you can write as sigma I equal to 1 to fj of ai xi, and that's equal to ai fj of xi. Just expand the sum and all other terms are 0 except this term aj fj of xj. Fj of xj 1, therefore this is equal to aj. Therefore fj of xj equal to aj. This implies fi of x is equal to ai. So x you can write as sigma I equal to 1 to n fi of x xi. Okay. Hope this is clear.